Alright guys, I'm back with a quick lesson here about diagonalization. This is section 7.3 in our book. You know, I had a couple of lectures about defective and non-defective matrices. I haven't really told you yet why we care about having a non-defective matrix. A non-defective matrix is a good thing. We like that when our matrix is non-defective, but I need to explain kind of why. You know, we need to understand, of course we're going to be seeing for the whole rest of this course why eigenvalues and eigenvectors are important. Even when we go back to differential equations, we're going to see why they're important. But I want to give you at least one good reason why we care about eigenvalues and eigenvectors in an application setting in this section. So diagonalization is a great application of eigenvalues and eigenvectors, and in particular of having a non-defective matrix. Okay, so let's suppose that we have a non-defective n by n matrix. Incidentally, if your matrix is defective and you want to do something like diagonalization, you get to take Math 307 to learn about that. So there is some hope even for a defective matrix, but it's a bit more complicated. So we're going to save that for when you become math majors and you take Math 307. You'll see what I'm talking about. Okay, but let's just focus on non-defective matrices for this particular video. Remember what that means. That just means that we have n linearly independent eigenvectors. So let's actually write them down and get some notation going. So let's let v1, v2, up to vn be n linearly independent eigenvectors of the matrix capital A. Okay? That's what it means to be non-defective. Every eigenvalue pulls its weight. The dimension of each eigenspace is equal to the multiplicity of the eigenvalue. That's for each eigenvalue. These are just different ways of reminding you what non-defective means. Okay? So here's what we are going to do in this quest to understand diagonalization. I'm going to build a matrix. I'm going to build a matrix. I'm going to call it S. And what I'm going to do is I'm going to put these eigenvectors into the columns of this matrix. Okay? Now this matrix has n columns. Each one of these columns is filled by an eigenvector. Those eigenvectors are vectors in Rn. So they have n slots each. So this is actually an n by n matrix. We have n columns, and each column has n slots. So that means there's also n rows. Okay, so we're going to build this matrix. Now, because these columns are Li, one of the things we know is that this matrix is therefore invertible. So S is an invertible matrix, and in a few minutes we're going to see the S inverse showing up in the problem. Okay, so we're starting off with this matrix. Now here's what I want to do. I would like to make a calculation. So just a little theoretical thing for a moment, if you guys will bear with me. I'm going to take the original matrix A and I'm going to multiply it by this matrix S that I just wrote down. Okay, so what is that? Well, that's just A times the matrix whose columns are these eigenvectors. So that's just A times S. Okay, but now let's imagine doing the multiplication here. Now remember what you do, you go across, we're doing a multiplication, you're going to go across the rows of the first matrix and down the columns of the second matrix. So as you're doing these calculations, do you guys see that basically the first column of this product is just A times V1, right? A V1. And the second column is just A V2. And so on and so on and so on, A Vn. Okay, so it's going to look something like that. Okay. Now each one of these eigenvectors, of course, has a corresponding eigenvalue. Let me just put those eigenvalues right here. Lambda 1, lambda 2, etc., up to lambda n. They may or may not be distinct. Remember, if all of the lambdas are distinct, then the matrix is definitely non-defective. But even if some of these lambdas are the same lambda more than once, as long as that eigenvalue is pulling its weight, okay, which is what we're assuming here, then we're okay. This matrix is still non-defective. Okay? So those are the eigenvalues. So of course what we know, the most important equation, right, is that AV equals lambda V. This is the place where we started this whole chapter off with. AV equals lambda V. So I'm going to plug that in right into here now. I'm going to change this to lambda 1 V1 and lambda 2 V2, etc., etc., etc. Okay? And the last one being lambda n Vn, like that. Okay? Now, what you've basically done here is you have multiplied each of the eigenvectors by the corresponding eigenvalue. And what I hope you will agree with is that we can achieve that matrix by instead first writing down the original matrix S and right multiplying it by a diagonal matrix with the lambdas going down the diagonal. So zeros everywhere else, but with, yeah, that looks good. Just making sure that you guys can see that on the screen there. So this is just lambda 1, lambda 2, all the way up to lambda n, like that. Okay, so does this kind of make sense? Like if I have, let's just take an example. If I have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and I multiply by the matrix -1 and 2 and 3 or something like that, right? Everything else being zeros here. If you just do the calculation here, right, what's going to happen is you're going to get the negative of the first column. You're going to get 2 times the second column. Okay, 2 times the second column. And then you're going to get 3 times the third column. Okay, when you right multiply by a diagonal matrix, what essentially happens is that the columns of the matrix on the left get scale multiplied by those corresponding diagonal entries. This example kind of illustrates that. Okay. The point is that therefore this, I'm going to work my way up here for a moment. This is just S times a diagonal matrix D, where D is this matrix right here. Okay, D is the diagonal matrix that has the corresponding lambdas going down the main diagonal. Okay, so what do we actually have here? We have, if we look at the whole totality of this calculation, what we have done is we have said that A times S is equal to S times D. When you have a non-defective matrix A, you can make this equation. The columns of S are the eigenvectors. The diagonal entries of D are the eigenvalues. Okay? So in fact, you can take this equation and you can solve it in 2 ways. Let me show you both ways here. You could, for example, solve this for A. If you solve this for A, that means you need to right multiply on both sides of the equal sign by S inverse. So one way of expressing A is as such. So S times D times S inverse. Okay? That's one thing you can do. Another thing you can do is you can solve for D. So to do that, you would left multiply by S inverse on both sides. So you would have S inverse A S equals D. So both of these equations are correct. And when you're trying to learn them, you need to be a little careful which side the S inverse is on, okay? When you've solved it for D, the S inverse is on the left side. when you solve it for A, the S inverse is over here on the right side. So the formulas look a little bit different. Please remember that you cannot cancel S with S inverse unless they are right next to each other. Right? So S times S inverse cancels out to the identity matrix. But S with a D sandwiched in between it and then an S inverse does not cancel out. So we really have to leave it just like this. Okay, now there are going to be problems in the homework that are going to say, the problems in the homework are going to say, find S and D such that S inverse AS is equal to D. I just want to clarify, you don't actually have to worry about calculating anything here when you're doing those problems. You just need to do this. Find the S, which is very easy. It's just the matrix whose columns are the eigenvectors. And find D, which is even easier. You just write down a diagonal matrix with the corresponding lambdas down the main diagonal. You just do that. The theory that we just presented shows you that the relationship between the S and the D and the original matrix is this. But they're not asking you in those homework problems to find S inverse. You don't have to do that. Okay? Or to do this multiplication. I don't need to multiply S inverse times A times S because after all I know what it's going to equal. It's going to equal my diagonal matrix D. Okay, so let me just do an example of this with you. And I'm going to use a matrix that I've used before in another video previously. So I'm going to consider the matrix, let me see if I think I called this matrix, I don't actually remember what I called this matrix before. Let me just call it A for right now. It might not be the same matrix. I may have called it B last time. But let me just call it A. It's this matrix here. We've seen this one before in the earlier video. 2, negative 5, 5, 0, 3, negative 1, and 0, negative 1, 3. Okay? Let's do the following thing. Let's find S and D such that S inverse AS is equal to D. I'm going to refer you back to the earlier examples, though, in terms of what the eigenvalues and eigenvectors were. So I'm just going to recall for you here, so that we save some time. I don't want to redo all of that work that we had done before. That the eigenvalues were 2, 2, and 4. Even though we have a repeated eigenvalue, this matrix, as we saw earlier, was still non-defective. So we had a basis, I'll just remind you, a basis for the eigenspace corresponding to lambda equals 2, and that basis was 1, 0, 0, and 0, 1, 1. You can, of course, recheck all of these calculations if you want to. And then there was also a basis for the eigenspace of lambda equals 4, which was 5, negative 1, and 1. Okay? So once you have this information, it's very easy to do this problem and to find S and D. S is simply the matrix where the eigenvectors go into the columns. You just write it down, okay? And again, don't try to find S inverse right now. That would actually take a fair bit of work. You remember we learned how to find the inverse of a 3 by 3 matrix a number of weeks ago. But right now that's not what they're asking you to do. They just want you to write down what S is. And then the D, of course, is the matrix, is the diagonal matrix that has the eigenvalues down the main diagonal. Now, sometimes I won't write all the zeros in on these matrices. So if I just write the numbers on the diagonal like that, you're supposed to assume that everywhere that there's a white space, you would have a 0. Okay? Now, this is not the only correct answer, because it's also okay to put these eigenvectors in a different order. So we could have said, you know what, I'm going to put 0, 1, 1 first, and then 5, negative 1, and 1, and then 1, 0, 0. You can do that. These eigenvectors are in the columns. The only thing is, of course, you won't be surprised that then when you write down your diagonal matrix, right, now the eigenvalues have to be reshuffled in a corresponding pattern. So the third column originally corresponded to lambda equals 4. Well, now that's the second column. So as long as your two things are matched up right, it's okay. And either way of doing this is acceptable. Okay? Does this kind of make sense, I hope? I guess you can't answer that question. Hopefully it makes sense. If not, be sure to ask me. You can shoot me an email, send me a note, I'll try and help you out. So I still haven't really explained, so what is this good for? All right, so we can diagonalize our matrix. By the way, that reminds me. So with this illustration, what we've really done is we've sort of taken the A and we've associated it with a diagonal matrix. So we're going to say that the matrix A is diagonalizable. So definition, A is diagonalizable if we can find S and D with S inverse AS equals D. But you know what? In order to find S and D, you're really just saying that you have to have n linearly independent eigenvectors. That's how we were able to make the matrix S. We had enough columns to make a full square matrix out of S. So the point being that being diagonalizable really just means that the matrix is not defective. It has n linearly independent eigenvectors. So what I want to make clear, because when I first learned this stuff, I was a little confused. Diagonalizable is the same thing as non-defective, right? They are exactly the same thing. There is no difference in the definition. It's a little frustrating because we don't like to have two definitions for the same thing. Because like, why would you have two definitions for one thing? But that's just the way this particular topic has developed, okay? Non-defective just means every eigenvalue pulls its weight. Assuming that happens, you can diagonalize your matrix in the sense that I wrote right here. Okay, S inverse AS is equal to D. Okay, so the question might still be, so what? You can diagonalize your matrix. You can make this equation, all right, this is the equation that I'm talking about. You can make an equation like that. Still, the question remains, so what? What is this actually good for? Well, just as a quick application of this, in this example that I just did, what if we asked, what is A to the 2017th power? Okay. A times A times A times A. We want to multiply this matrix by itself 2017 times. Okay, well, not that we're actually going to come up with an answer right now, but I just want to show you where the diagonalization process could actually help you with that. Okay, so here's the thing. If I wanted to calculate A to the 2017th, what I can do is I can say, wait a minute, A is the same as SD S inverse. Remember from earlier the equation for A was equal to SD S inverse. So if I want the 2017 power of that, I can think of it this way, right? But what is this? This is just SD S inverse times SD S inverse times SD S inverse, dot, 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 a whole bunch of times, right? In fact, 2017 times. But what you'll notice once you've actually sort of laid that out is that you do have S inverses next to S's. you have a lot of places where S inverse is directly next to S. And therefore, you can cancel the S and the S inverse when they're right next to one another. Okay, so what you can do here, guys, you have an S, and then D times D times D times D a whole bunch of times, 2017 times to be exact. And then there's one lonely S inverse at the very end over here. Okay? And we have right here on the board, we've written down, let me just come over here so I don't have to erase what S is. S is, well actually, let me just use the bottom formulation, then I can keep it on the board here, right? We actually have a way of setting this up. Here's S, 0, 5, 1, 1, negative 1, 0, 1, 1, 0, and then the matrix 2, 4, 2, that diagonal matrix to the 2017, and then S inverse, which I honestly don't know what that is right off the top of my head. We could work it out, of course. It's a 3 by 3 matrix. The thing is that the 2017th power is at this point only being applied to D, to the diagonal matrix D. And if I take, so I can leave the S by itself. If I take 2017 powers of this matrix here, you see what you're going to get, guys, is 2 to the 2017, 4 to the 2017, 2 to the 2017 on the main diagonal. In other words, it's easy to take a high power of a diagonal matrix, right? And so now with that information, I can figure out the 2017 power of A itself. Okay, so there are some computational benefits to diagonalization. There are some, if I have a matrix and I can diagonalize it, right, if I can apply the SDS inverse formula to it, then that helps me to simplify these kinds of calculations. Let me show you one more example of this process, okay? What I'm going to show you in this next example is something called a Markov process. Okay, I just want you to see, this is a really nice application of diagonalization. So let's do the following thing. I'm going to write down a little bit of a word problem here. So each day, 20% of the students in Professor A's class switch to Professor B, and 10% of the students in Professor B's class switch to Professor A. Okay, so we have these two professors, and these students are switching back and forth between two sections of a class. And let's assume that nobody drops, okay? Nobody ever drops the class, but they keep switching, and they do this every single day for the whole semester. So the question is, at the end of the semester, that's really like saying t goes to infinity. Okay, I'm sure by the end of the semester it feels like an infinite amount of time. The question is, what fraction of students are in each class? Okay, so let's see if we can answer that really quickly. We can use diagonalization to do this. Okay, let me show you how. What I'm going to do, I'm going to create a vector, x of t, and that's going to represent a of t and b of t, and these are going to be the students that are in each class on the tth day. Okay, so a of t is the number of students in Professor A's class on day t, and b of t is going to be the number of students in Professor B's class on day T. Okay? Hopefully makes sense so far. So what we can do is we can try to figure out, well, from one day to the next, how does A of t and B of t change? Okay, and I can actually represent this as a matrix. Okay, so I'm going to put A of t and B of t right here. Let's say those are the numbers of students in the two sections today. And what I want to know is, well, how many students will Professor A and Professor B have tomorrow? One day later. I'm adding one day here. Okay? So one day later, how many students will Professor A have and how many students will Professor B have? Well, the truth of the matter is that Professor A is going to keep 80%, that's 0.8, 80% of however many students he has today, he will still have tomorrow. Plus, he's going to pick up 10% of Professor B's students, because 10% of Professor B's students are going to switch into Professor A's class tomorrow. Okay? Similarly, how many students does so see what we're getting here, guys, is that's the number of students in Professor A's class tomorrow. What about Professor B's class tomorrow? Well, he's going to pick up 20% of Professor A's students and keep 90% of his own students. Okay? Every time I multiply by this matrix, call it capital A here, every time I multiply by this matrix, I essentially take this vector and I add one day to it. Right? So if I multiplied twice by this matrix, I would be effectively looking at how the distribution of the students looks 2 days forward. Right? If I cube the matrix, 3 days forward. And so on and so forth. You're calculating how many students are in each professor's class, however many days forward you want to calculate. So what I really need to do here is we need to figure out what a to the infinity power is, basically. Okay, that's a high power of this matrix. So I'm going to try and diagonalize this matrix. Okay, hopefully it's diagonalizable. So let's get to work and try and do that. So to diagonalize the matrix, I've got to go through my whole procedure. I have to find my eigenvalues. So I'm going to subtract lambda from the main diagonal here. Okay. So we have 0.8 minus lambda and 0.9 minus lambda on the diagonal. The other two numbers stay the same. I just do this, this is a 2 by 2 calculation, not too bad. Luckily, we don't have 3 professors with 3 sections. That would be definitely more work. Okay, so this would be the kind of expression we get if we do the AD minus BC thing. Okay, and when you work this out, you're going to get lambda squared minus 1.7 lambda plus 0.7. Okay, and that actually factors very nicely. Lambda minus 1 times lambda minus 0.7. Okay? I'm going to erase the question now. Notice I have 2 distinct lambdas. There's no repeats here, so this is going to be a diagonalizable matrix. In other words, it's a non-defective matrix. Okay? So let's try to look at each eigenspace. Lambda equals 1. And then we'll do lambda equals 0.7. We have to find the corresponding eigenvectors now. Okay, so I'm going to look at the null space of the matrix that I get when I subtract 1 from the main diagonal. I'll have negative 0.2, 0.1, 0.2, and negative 0.1. Okay, this matrix is always not invertible. I'm going to cross off a row. It doesn't matter. I guess I'll cross off this row. It doesn't matter which row we cross off. Okay, one of them is going to get zeroed out. And then I'm going to make an eigenvector by doing that trick that I showed you in an earlier segment, where I'm going to swap these 2 entries. I'm going to swap these 2 entries and change the sign of one of them. Let me just make sure that I'm doing it the same way both times. I'm going to swap these 2 entries and make them both positive. And I'm also going to multiply through by 10. I'm going to get rid of